I'm Sherf. I'm the data science team lead at the BlueGreen Water Research Center at BlueGreen Water Technologies, and welcome to the webinar. Today, I'm going to talk about a new study we've conducted here at BlueGreen on a new global deep learning framework for high-precision harmful algal bloom assessment. The study was conducted with co-authors Bar Efrati, Gabe Rosen, and Moshe Harel. You can find the original manuscript, which this study is based on arXiv in this digital number. So let's start. Now, remote sensing for worldwide HAB monitoring. Why do we monitor HAB with remote sensing? Because it provides us a continuous monitoring. And we know that HAB are increasing worldwide, and they are rising cost in terms of ecology, economic, and public health impact. Now, remote sensing supports large-scale HAB surveillance. However, accurate chlorophyll-a retrieval remains difficult due to various optical interferences. We also know that many of the existing algorithms in literature are regional specific, and it is difficult to tune them to other places. Since we want a global model that can be scaled to other places and to retrieve chlorophyll-a with accurate, we have developed a three-stage machine learning framework that delivers a robust, globally transferable chlorophyll-a mapping without the need for regional tuning. The main challenges in monitoring harmful algal bloom for space mainly come from several reasons. The first is imaging artifact, because we know that data is frequently incomplete due to cloud, sunlit, there's shadows, ice. We have also other optical interferences such that the true chlorophyll-a signal is often masked by non-algal particles like turbidity, sediments, and sedum. And these particles mask the true chlorophyll-a signals, which prevent us to retrieve the accurate value and leads to error in the result. On the other hand, we also have extreme concentration. At very high densities of algae, what we call SCAM, we have an optical saturation, and we cannot retrieve the accurate value. And on the lower regime, at low concentration sensitivity, we know that standard atmospheric correction, like the send to core adopted here in the study through the Google Earth Engine, performs poorly in clear water with low chlorophyll-a levels, which increases the error. And lastly, as previously mentioned, the lack of generalizability, because most of the existing algorithms are regional specific, and they're tuned for lake or specific region. For this reason, we applied the Global Water Classifier, which generalizes this result and allow us a scalable monitoring of harmful algal bloom. So the Global Water Classifier is a supervised, geospatially extensive machine learning classifier, which is the first stage and the crucial stage in the retrieval chlorophyll-a. This stage removes instrumental and environmental interferences. Now, what the Global Water Classifier does, it outputs the analyzable water pixels, those pixels which possess a clean spectral signature that we want to analyze. In other words, it distinguishes water across varying chlorophyll-a levels. It means that if you have water with varying algae densities, between non-water speckle that we don't want to analyze. So it does this binary classification. It was trained using Sentinel-2 on the relevant bands on over 100 different water bodies worldwide. Now, let's go on and go over how we build this classifier, and let's start to understand the type of optical interference that we have. We have a nature-based optical interferences, we have instrumental-based, and we also have a modeling interferences. Like by modeling, I mean bad atmospheric correction or inappropriate atmospheric correction. Instrumental is the sensor noise error inherent to Sentinel-2 satellite, and the nature-based is the one that you see here. For example, we have clouds, shadows, sunlit, ice, snow, aquatic vegetation, sediments, and also clean water. Now, let's go over and break down those interferences by looking at the spectrum of them, and in this way we understand how we build this classifier. So here we can see an example of clouds, and we see the huge elevation at the Nil. This is the Pyramid Lake at Nevada. Here we see sun glint. You can see the pixel, that orange box. So sun glint actually increases and shifts all the spectrum up and makes it uniform. Here you have two types of algae densities, low and high. You can see that algae is most pronounced at the red edge regime, and you can see the large deviation here and the increment in this regime, especially at the high. You can see the huge elevation at the red regime. You have also snow with very, very strong albedo. Everything is elevated up. You have aquatic vegetation, strong absorption in this regime, and large reflection at the near. You also have sediments. Now, sediments is a bit tricky, and they are very, very efficient chlorophyll-a masker because they have, again, strong reflectance at the red edge. However, they also have the strong reflectance to the green. So if you see this flatness at the green red edge, it means that you have sediments in many cases. And of course, we also have the clean water spectra, the one that we want to analyze. Here you can see a very clean water spectrum. This is Crater Lake. It's very deep, so it's very pronounced. This beautiful attenuation of water, strong reflection in the blue, and goes down. And here you can see a lens spectrum, and again, large reflection at the near. Now, by looking in this, we interrogated the specific spectral signature from 100 different water bodies, validated them, and built this classifier by assigning them which is assigned to the positive class and which belongs to the negative class. But why we need a machine learning framework for this? Because threshold-based classification are often fails. And why they fail? Because of threshold-based spectral indices such as NDWI, ICE indices, and SUNGLIT, which are often used in those studies, fail in clean water, in thin ice, or weak lint. These are subtle scenes that display small deviation from clean water spectrum. And they fail because they don't capture a small deviation. We also have vegetation and sediments, which are very good in mimicking algal bloom spectrum. And under certain wavelength, they cause infrequent misclassification. We also have high optical variability across lakes, between different lakes. So the spectrum is not generalized to different lakes. And the last reason that we mentioned previously is the inconsistency of atmospheric correction that display error all the times. And for this reason, machine learning techniques can capture the large variability in optical conditions and generalize across diverse scenes where fixed thresholds fail. And this would be the advantage and the strength of the machine learning framework in capturing this nonlinear behavior. For example, threshold-based methods fail in clean water in these scenarios. You can see it here, mantra reservoir, here in dense algae, which is misidentified, and also here in clean water, misidentified. Another example here in Doctor's Lake, Milton Reservoir, Hardbisprot Dam in South Africa, where also aquatic vegetation were misidentified as algal bloom. So for this reason, we developed the classifier that will allow us to identify the correct water pixel. This is the general workflow of the Global Water Classifier. It established and built it from 3 different stages. The first is a binary classification on the 100 different water bodies. We assign a positive class and negative class. So the positive is water pixel across chlorophyll-a, and the negative is cloud, sunlit, snow, ice, vegetation, and more. We train a random forest classifier to identify them and to distinguish between them as a binary classifier. Now, when during the update of the model, we developed a dynamical update approach where we added new data in small batches. Now, this new data is significant than this type of data, than cloud, sunlit, because the new data that was added is composed of small spectral deviation. These are subtle scenes that might not be captured by threshold-based method and will be captured by the machine learning framework. So to ensure the consistency and the correctness of the model, we added small data set with small deviation, retrain it, and check if the model performs well and the consistency of the model. So in the performance test, we maintain precision and recall about 97.8, and we tested the older model, machine learning model, with the new retrained model with the new subtle scenes added by calculating the model agreement and the individual probability alignment. So let's break it down. again, so we collected data for 100 different water bodies, we trained it, and we label it. Positive class is water pixels across different chlorophyll-a levels, and the negative class is for clouds, sunlit, snow, ice, vegetation, and more. We added new data on subtle scenes for low sediments, diluted aquatic vegetation, thin ice layers, thin clouds layer, very weak glints. These scenes might not be captured by threshold-based, but are captured by this method. And the model was updated and retrained. And in this way, we expanded the dataset and improved the sensitivity to find spectral variations. We ensure performance stability by these quantities, agreement, Cohen's kappa, and more importantly, the individual probability correlation. So we made a direct comparison of per sample confidence for each probability that is outputted by the random forest classifier of each scene. We compare it to the probability of the new retrained model with a subtle scene, and we saw how differ are they. Luckily, that was not the case. They were very similar. And in this way, the dynamical workflow preserved the desired accuracy performances and the sensitivity to the environmental changes. You can see the result of the previous images here. In this way, the Global Water Classifier is able to identify the water correctly, the dense algae, very high density of algae, very good. Also here, this is a thin ice layer which is misidentified. Also in this case, this is the threshold-based, and the Global Water Classifier identify well the clouds, the water pixels correctly. Also here, and also here. Now, having established a Global Water Classifier, we have overcome the main challenge, the noise. We have a method to achieve a clean, good data that we can analyze, and with this we can retrieve the good and accurate chlorophyll-a value and monitor on HAB accurately. So the next stage would be to use the Global Water Classifier as the first stage of filtering the data and cleaning the data, and to match up it with in-situ water samples and develop a deep learning framework for chlorophyll-a retrieval. So what we did, we used the USGS AquaMatch dataset and performed ground truthing on more than 13,000 samples. In total, over 867 different water bodies across the United States. This is the geographical spread of them. Very large variability between different lakes in different regions. The way to do this is for each point in the USGS AquaMatch dataset, we have the coordinates, we have the date, and the chlorophyll-a value measured sample. For this point, we extracted the relevant indices, spectral bands from Sentinel-2. We do this matchup and calculated these 12 spectral indices, which allow us to get more data and improve the model performances. We have the indices that facilitate the identification of clean water pixels, good water pixels. We have the water index, the vegetation, the algal bloom index, turbidity, 2 types of sedum indexes, sediment indexes, and another types of algal bloom identifier. We also have this one, the FAI, which is the floating algae index, and it tends to be a very important index that allows us to identify those thin layer of scums, especially on top of clean water. So we applied the Global Water Classifier on the USGS dataset. We extracted the chlorophyll-a values for each 13,626 points and calculated these spectral indices. Now, and then we calculated, we used an XGBoost regressor to retrieve the true chlorophyll-a value. So again, we apply the Global Water Classifier, and then for each pixel, we have only the reliable water scenes for chlorophyll-a estimation. So we have the positive class and the negative class. The positive class is the type of pixels that we want to analyze, and the negative is the one that we don't want. Now, within this negative class, we have the near zero score, the one that display very strong deviation for clean water, and those scenes were identified by threshold-based methods. And I'm talking about clouds, glint, snow, ice. They were removed by threshold-based. So we removed them from the data, And in this plot, we made a comparison between the positive class and the negative class, excluding all near zero cases. And we keep many scenes the threshold method will not discard. So what you see here is the impact of the global water classifier, where blue points assigned to the positive class and red to the negative. And you can see at the table the huge improvement of the positive class over the negative one, which in some cases led to more than 50% improvements in accuracy, in R-squared terms, mean absolute error, root mean square error, logarithmic, and percentile errors. And the conclusion is that the global water classifier impact is that clean data leads to dramatically better predictions. And this is the cornerstone that allow us to improve the results significantly. Now, in the next stage, we focused on the positive label pixels, the water pixel that we want to analyze, and we made a residual analysis of them. Because when we look at the relative residual in percents with respect to the chlorophyll-a, we noticed that error pattern differ from approximately below and above 10 milligrams per cubic meter. In order to display it and to correctly, we measure two different quantities. We measure the coefficient of variance below 10 and above 10, and the Shannon entropy. Now, the coefficient of variance tells you the spread around the mean, and the Shannon entropy of the residuals tells you how evenly the errors are distributed or how uniformly. So higher entropy means that the residuals are more uniformly, and where the residual is more concentrated in some regime, in very small regime, it means that the entropy is very low. So we calculated the coefficient of variance and entropy above and below 10. And not surprisingly, we saw this huge difference that below 10, the variation in the data and the entropy are much larger than above 10. Though in both data regime, the entropy is not low and is not as high. It's not near zero. So it means that inside the error pattern, we have some pattern. We have some structure error in the data that we might capture by a more sophisticated method. Okay, so the conclusion from this result is that the residual analysis tells us that you have an error that is structured in the data, and it is possible to capture it by some intricate method. For this, we use the residual convolutional neural network. This is the third stage. The first stage was the global water classifier, the classification. The second stage is the regression, where we get the chlorophyll-a value. And here, we learn the residual structure by a residual convolutional neural network. As I said, the structured nature of these errors suggests that they require a more focused treatment. Now, instead of learning the full mapping, as in the XGBoost regression, where we train the data on the chlorophyll-a and retrieve the predicted chlorophyll-a value, we train it on the residual. And why we can do this? Because we now know we have the predicted chlorophyll-a value from the regression, and we can train it on the residual compared to the in situ value. So we train it on the deviation, normalized deviation of the prediction to the true, the normalized one. And the output is the error, the prediction. And from the output, we corrected the XGBoost prediction by this formula. Now, since the errors behave differently in these two regimes, we train independently on each regime. This is the RCNN architecture, which employ a resonant light architecture, where in a resonant light architecture, we have the skip connection that allows you to train and to be more sensitive to small deviation. You inform the output of this residual block on the input. So the input is transferred forward, and this way you mitigate error and you allow to yourself to be more sensitive to small deviation and to correct the error. This is why it's called an RCNN. Of course, you can find more details about it in the manuscript. And this is the three-stage retrieval workflow. In the first stage, the classification by the Global Water Classifier, we built the classifier and we applied it on the USGS dataset. In the second stage, we applied it on the USGS dataset by using XGBoost regression. So we extracted the Sentinel-2 bands, we calculated the spectral indices, and we retrieved chlorophyll-a values and obtained the prediction. In the third stage, we took this prediction and calculated the residual, the error of this prediction compared to the original value. And we trained the RCNN on the error. From the RCNN, we derived the prediction error, and we updated the prediction and corrected the original prediction from the XGBoost by this formula. The final results are these. This is the linear scale and the log scale results. The results are rather impressive, as I'll show you soon by comparison to other models. In terms of R-square slope, mean absolute error, root mean squared error, and logarithmic error, the slope is very close to 1. R-square is nearly 0.08. And also the logarithmic error, which is very impressive. And again, in this data, you see here more than 2,000 test points on 867 different water bodies with a huge optical diversity that was captured by this three-stage workflow. Now, to ensure the performance of a model, to understand it, I also tested a residual comparison between the older model before the RCNN and after the residual analysis. And you can see the huge improvement down to residual analysis. So the conclusion is the RCNN correction stage, it delivers significant gains in accuracy and reduces absolute error by over 30%. And it proves the effectiveness in the third stage and the crucial of the third stage. Yeah, you can see how the coefficient of variance and entropy improved in the stage after the residual convolutional neural network. Okay, now let's go to a performance demonstration of the original images that I showed you previously with the chlorophyll-a mapping, the accurate one. You can see how glint pixels accurately removed. And also here you can see the clouds removal, very efficient. In addition, you can see algae in different densities, and also at very high densities, accurately identified. Also in this case, you can see the sediments removal, snow and ice removal, water vegetation. So this is a new performance benchmark for global water quality monitoring. Here in BlueGreen, we have a tool that allows us to monitor HAB globally with high precision results. You can see the comparison to other state-of-the-art models, which most of them are regional specific, and our results in some places comparable, in some places smaller or better by a fraction of percent, but we have achieved this transferability and globality of our model, which allow us to use it in many different scenarios and optical variations. And that's all. So thank you very much. You can reach me out by this email. Thank you.